Hello everybody, welcome back to AP Physics. We're going to work on this problem this morning. Hopefully you can study it and get better to solve problems. So here's what we have. We have a snowball of radius r and mass m and moment of inertia equal to 2/5 of the mass times the radius squared that rolls without slipping down a hill. The ball stays the same size. Something that I missed in this problem is to say that the height of this hill is h. Now every time we see radius r, mass m, that represents an actual number. It represents something that we actually know. I know we don't have the exact precise value, but we know radius is r. It's a quantity that we know. Okay, so we're going to start by doing a little drawing. So here's our hill. And that hill has a height equal to h. Okay, from that hill, we have a ball falling. It's a snowball actually that is rolling without slipping. So there's some information that we know because of that sentence, rolling without slipping. The next part says, at the same time, a sled with a kid together with the same mass than the snowball slide down the hill with no friction. Which one will get faster to the bottom of the hill? Which one will be traveling faster at the bottom of the hill? I think if we work the second question first, we will know who or which object gets to the bottom faster than the other one. One of the biggest issues I have seen with this type of problems, or with any problems in general at this point for physics, is students do not know what concepts to use. At this point, we have seen so many different tools, so many different topics that you don't really know what to use. So you're thinking, okay, should I use kinematics? Should I use forces? Should I use, I don't know, projectile motion, which definitely this is not projectile motion. Should I use concepts of momentum or maybe energy? So that is something that you have to decide which tools you will be using. So at this point, let's start just thinking about what is the concept that we would use. Let's start with kinematics, for example. We are trying to determine the velocity at the bottom. So a lot of the students told me, why don't we use velocity equals distance over time? Well, number one, we do not know the time. Second, we do not know the distance. And third, this equation is for motion that is constant. So if the motion is constant, you can use this equation if you have all what you need. But in this case, the motion is definitely not constant. As the objects are moving down, as the objects are going in this direction, they are speeding up. So you cannot use this equation, definitely. So let's go back and get rid of this one. Somebody else told me, okay, what about if we use acceleration equals to the change in velocity over change in time? One more time, this is about kinematics. This is one of the kinematic equations. If you think about it, this would be, what is the final velocity? If we know the initial velocity, we know the acceleration, and we know the time. So yes, you can think about this equation to find a final velocity, but guess what? You do not have an acceleration, and you do not have a time. Of course, you know that the velocity in the beginning is equal to 0, but you don't know these two things. So you have to think about what information you have and what equation you can use. There are many different options. The decisive detail is what information I do have. The information that we do have is the radius, the mass, the moment of inertia. That is what we know. Oh, and the height. Okay, so this equation is not good, so let's get rid of that equation. Now let's keep working on the different equations and see which one can we use. Okay, the next part will be, what about Newton's second law? So sum of the forces equal to the mass times the acceleration. This one doesn't even have velocity there. So definitely I cannot use this equation. This is not something I can use. It will not help me to find the velocity. Okay, let's keep moving. So now we have momentum. What about the equation for momentum or conservation of momentum? Yeah, this one has velocity. This one has the mass of the object, so I know the mass, but I do not know anything about momentum. So again, that's not the good equation to use. It's not a good tool. So let's get rid of this one too. The last concept that we have seen so far, kinematics, forces, projectile motion. This is not projectile motion. Momentum, energy. So let's go to energy. What types of energies do we have in this problem? Well, if you think about it very carefully, at the top you have potential energy. And that potential energy is transformed into a different energy. By the way, both objects have the same potential energy because they both have the same mass, the same gravitational acceleration, and they have the same height. So they both have the same potential energy due to the gravity at the beginning, right before they are starting to slide down that hill. Now, what else do we know? Well, we know that there is an energy conservation. That energy conservation that happens makes this potential energy transform into kinetic energy. In the case of the snowball, we will have the two kinds of kinetic energy. We will have the rotational kinetic energy because it's spinning, and the translational kinetic energy because it is moving down that hill. Okay, so now in the case of the sled, we only have translational kinetic energy. Now, how do I know that these are the equations that I need to find the velocity? Well, if you notice, if you remember, kinetic energy is 1/2 of the mass times the velocity, linear velocity, square. This velocity is the one that we need. And notice we have all the information. We know the mass of the object. We know the height. We know the acceleration due to the gravity. And that's it. We don't need anything else. So let's use energy conservation concepts. So now my next question is the energy conserved? How do I know if energy is conserved? Okay, let me see. Here I'm missing my final kinetic energy for translational kinetic energy for the sled. Okay, how do I know if the energy is conserved? How do I know that? I know that there is an energy transformation that tells me that all the potential energy that is up here will be transformed into kinetic energy. But how do I know that everything is conserved and nothing is getting lost to friction, for example? Well, in the problem it says that down the hill is sliding, the sled is sliding with no friction. So I know that friction is not taking energy away. Now, something else that I also need to check is if there is a force doing work, then the energy will be changing. Now, are there any forces doing work on the objects? You may be thinking, well, the force of the gravity is pulling them down. So, yes, you're right. The force of the gravity is pulling those two objects down. But remember, if we include the Earth in our system, the Earth is pulling on both objects, and those two objects are pulling up on the Earth. And if all of this is our system, then those forces are internal forces, and we don't have to worry about them. So let's continue with the idea of the energy being conserved. Okay, so at this point, we know that we have to work with energy. We know that the energy needs to be conserved. That means that potential energy gets transformed completely into kinetic energy. So now the next step is go into my formula chart and actually look at the different equations. The equation for potential energy and the equation for kinetic energy of the translational kind. And that is what I'm going to do. I'm going to say mgh, mass, gravitational acceleration, and height, which is equal to the potential energy, is equal to the translational kinetic energy, which is 1/2 times the mass of the object times the velocity of the object square. Remember, what we are trying to find is how fast the object is traveling at the bottom of the hill. Which one of the two is actually traveling the fastest? That is the goal of this problem. So once I have this equation right here, what do I do with it? I'm looking for the velocity. So let's rearrange and solve for the velocity. But first, notice that the mass is in both sides, so we can cancel the mass out. And once we cancel the mass out, we can rearrange to find the velocity. And the velocity is going to be 2 times the acceleration to the gravity times the height. You can pause the video for a moment and try to do that rearrangement on your own to see if you can get it. That would be pretty important. Now, we're going to the second stage, the second part. So far we know the velocity of the sled when it's going at the bottom of the hill. Now the second part is knowing what happens to the snowball. So the snowball has an energy transformation too. That energy transformation is this one that I'm showing right here. So potential energy equals to translational kinetic energy and the rotational energy. Remember, all the potential energy is transformed into those two types of kinetic energies. Now, same way that we did with the last problem, with the last section, we are going to make a substitution of the equation. So I know that for potential energy, this is the mass times the gravity times the height. Then for the kinetic energy is 1/2 of the mass times the velocity square. Let me go back just to get rid of that little line, because that line is going to make us a little confused. Let me get rid of this line. Okay, perfect. Now, 1/2 of the mass times the velocity square. And then I have to use also rotational kinetic energy. I'm going to get rid of this line. Okay. And we will have 1/2 of the moment of inertia times the angular velocity square. Okay. So at this point, that is my equation. That is my conservation of the energy. The next point is get rid of everything that we don't know. Actually, before canceling all the masses and everything else, we need to check. There is here the moment of inertia and there is the velocity. We have to make a substitution. What is equivalent to the moment of inertia? So in the case of the moment of inertia, what I notice is that we have this expression right here. That is the moment of inertia for the snowball. So what I'm going to do is I'm going to rewrite my equation, and instead of the moment of inertia, I will write that expression that we have on the top. 2/5 of the mass times the radius square. The next step will be make a substitution for the angular velocity to put it in terms of the linear velocity. So if you remember, there is a little equation that says linear velocity is equal to angular velocity times the radius. So here's what I'm going to do. I'm going to solve for the angular velocity, and I'm going to say that is the velocity over the radius, and I'm going to make a little substitution there. So instead of the velocity, instead of the velocity, the angular velocity, I'm going to say linear velocity over radius. And by the way, it is squared. So it will be linear velocity v squared, this one, over r squared. Now I can start canceling everything that I have. So the first thing that I cancel is the radius square, because it's multiplying and dividing. Then I can get rid of the mass because it's in the three of those sections of the equation. The next part, I can cancel the number 2 is multiplying and dividing also. So once I cancel everything that I can cancel, I can get rid of, I can rewrite my equation. So I end up with something like this. This is gravity, height, equal to 1/2 of the velocity square plus 1/5 of the velocity square. Next step, I put those two things together. So 1/2 plus 1/5 is like adding apples. You have the v square that is common. So we end up with 7/10. So rearranging, actually, putting all that equation together, I have the gravity times the height equals to 7/10 of the velocity square. Now solve for the velocity. You can pause the video at this moment just to make sure that you know how to rearrange that little equation. So I'm going to have the velocity equals to 10/7 of the gravity times the height. Now think about it. Which object is going fastest? Which object is going the fastest at the bottom of the hill? This is 2gh. This one is 10/7. Think about it. 10/7 is like about 1.4. So definitely 2gh will be a greater number. So the sled is going faster at the bottom of the hill. Now, since it's developing a greater velocity, the sled will be getting to the bottom of the hill at a smaller time. It's traveling faster and it will use less time to get to the bottom. So that is the first part of this problem. Now the second part is kind of like the inverse situation. So it says, if both were moving on a flat surface at the same linear velocity, when I say both, I'm talking about the snowball and the sled. If they were moving in the at the same linear velocity and up to a hill, which one will get to a greatest height? So let me make my little picture. It is very important, guys, that you are doing a sketch for the problem, because the sketch will give you a better idea. It will give you some sort of a visual representation of the problem. That way you can understand it better. You can put all your given in that picture. So here's what I'm saying. Here's my sled, and then here's my snowball. They both are moving up. After traveling on a flat surface, they move up. They are starting the motion with the same velocity. So we are still working with energy. What is the energy transformation that is going on? Well, in this moment, you know that the sled has translational kinetic energy. The ball has translational kinetic energy plus rotational kinetic energy. So just think about it. Which object will get to a higher position? Let's just make up numbers. So if they have the same translational energy, let's say, I know I don't have any numbers, I'm just making them up. Let's say the sled has 2 joules of translational kinetic energy, And the snowball has the same kinetic energy, the same translational kinetic energy, because it's moving at the same linear velocity. So it also has 2 joules of energy. Whatever else it has as rotational kinetic energy will be adding to those 2 joules. So definitely the snowball has more energy available to go up, much more energy available. And since it has more energy available, it will go to a higher height. So maybe the snowball goes up to here, and the sled, it just goes up to here. The reason is the snowball has more energy available. Very nice. So that is it for this problem. I hope it is useful. Please pay attention, study out of this problem, because what is coming next, you will use this problem. See you later. Thank you for listening.